Right, primes. So a prime number is any positive integer with exactly two factors. So for example, 10 is not a prime number because its factors are 1, 2, 5 and 10. 1 times 10 or 2 times 5. However, 7 is a prime number because its factors are simply 1 and 7. But what if we have a very large number like 1, 2, 3, 4, 5, 6, 7? How do I know if that's prime? Well, we'll start off by doing something very simple. We're just going to try dividing it by every number less than itself and see whether any of those have no remainder. So let's start by saying our number, and what we'll do now is we'll iterate through every number less than that number. So let's call it n, and let's start at 2 because if we try and divide by 1 then it'll have no remainder. And what do we want to go up to? Num. Then we'll say if num divided by n. I'll have better variable names once it gets a bit more complicated. Is equal to 0. That's basically saying if n is a factor of num, then print not prime, and that should work. So let's run this. Here we go, not prime. Let's make it print the factor as well that it found. So this found that 127 times 9721 is our number. So it's not prime. But let's enter a number we do know is prime. 7. 7's prime. How about if we do 100? Not prime, because the factors of 100 are 2, 4, 5, 10, 20, 25, and 50. And of course 1 and 100, but there's no point checking those, because 1 and the number itself are the two factors it's allowed, because it has to have exactly 2. But my goal for this video series is to generate a list of prime numbers, not just check if 1 is prime. So I will make a new program and be back with you. Right, so now what we'll do is we will decide a limit that we want to find the prime numbers up to. So let's call that prime limit. And for now let's say 1,000. 100, make it a bit easier. 100 we can probably check the results. Then we're going to have a list where we store all of our primes. So now let's iterate through from 2, because we ignore 1, up to our prime limit, checking if each number is prime. So for num in range, and let's go for 2 to 100. Then for each number we need to go through another range, which will be from 2 to whatever the number is we're checking. And then we'll have the same thing we had before. If, I'll put some spaces in here, if the number that we're seeing as prime is divisible by the number by whatever we're trying to divide by, then let's make a variable, prime check. And if it is found to be prime, it's false. But that means we need to assume it's true and then prove it's not. So prime check equals true. We can get rid of this one. So for each number up to 100, beginning with 2, we assume it's prime, and then we go through every integer from 2 to that number, testing if it is divisible by that. And if it is, then it's no longer prime, so we set prime check to false. And what we'll do is then, once we've checked the number, if it is prime, so we'll say if prime check, then we want to add that to the list. So prime list num. Let's see if this works. Print prime list at the end. Oh look, we've got a list of prime numbers up to 100. Isn't that great? So in the next part we're going to be thinking about how we can optimize this program. Right, so now we have a program that can generate a list of prime numbers. What I'll do now is I'll add 2 extra things to it which just help with optimizing the program. And then we'll look at how to, they help with seeing how optimized it is, and then we'll work on optimizing it. So I'm going to start by adding a timer to the program that will tell us how long it's taking to run. So start time, and then what we'll do is at the end, but we'll do it before we print this, because if the prime list is, say, 1,000 primes not long, that will take time to print, but we don't want to include that because that's not actually in the calculation. So then we'll do print, how about we do end time equals time, and then down here we can print it afterwards. End time minus start time. Great. And then the other thing that I wanted to do is print out the length of the prime list so we can see how many primes there are. Why do we want that? Because once we start calculating primes up to a much higher value, it helps to know how many there are, because it's a lot easier. We can make the assumption that if we've calculated the correct number of primes, then they're probably all correct. And now we can set prime limit to a much bigger value, so we can see here this took 0.5 milliseconds to calculate the primes up to 100. So how about we try 10,000? And here you can see a problem. I've set this as 100 and not prime limit. And now it's actually starting to take some time. There we go. Here's our big list of primes, 1,229 of them. And it took 4.2 seconds. So let's try and speed that up. But first I will quickly check that this is the correct number of primes. So I can confirm that is the correct number. The program that I ran to check it does not add 2 to the list, for reasons that you will see shortly. Which is why this value is 1 less than the number that we found. So this takes us 4.2 seconds. How can we speed that up? Well, firstly, all primes except 2 are odd. So let's not bother checking if even numbers are prime. So let's start at 3 and count up in steps of 2. So then we'll be doing 3, 5, 7, 9, and so on. And let's run this and see if it saves much time. So you can see now we also don't have the 2 in our list if we scroll up to the top. But for missing one prime, we can just add that to the list. In fact, we can just put it in here, if that would make some of you happier. 1, 2, 2, 9, there we go, and now it's a complete list of the primes. And now we've almost halved the time it takes, 2.1 seconds. What else can we do? Well, if we find that a number isn't prime, we don't need to keep checking because it's no longer prime. So let's put a simple break statement at the end of that. Let's see if that saves us much time. Wow! Now we're under half a second, and we've still got the same value. What I will do is I will just stop it from printing the big list, but it doesn't matter. As long as this is 1229, we can be fairly confident we're correct. So now 470 milliseconds from 4 seconds, we've already taken an order of magnitude off the calculation time. But I think we can still go a bit faster. So if you imagine we're checking the number 25, we try dividing it by 2, no, try dividing it by 3, and then 4, and then 5, and of course it is divisible by 5, so we stop there. But if it wasn't, then we'd do 6, 7, 8, 9. But a factor of a number will not be greater than its square root. So, well, a factor could be, a prime factor couldn't. So I was debating whether to discuss prime factor decomposition, and I'm not going to, but I can quickly draw it on like some kind of number line, so I'll be back with you in a minute. So let's instead change what we are trying to divide to the square root of num. Let's see if that helps us. So you can see now we have a problem. We're finding more primes, and I believe if we have a look at our prime list, it will become quite clear what's going on. 9, 25, 49, they're not primes, but they are square numbers. This is because int, I think, rounds down, and we don't want that. And I can't remember how to not do that, so we're just going to add 1. And that should fix it. 1229. And now we've gone from, how long did it take us before? 0.47 to 0.01 seconds. So we're starting to get quite fast now. But there's another thing we can do to make it even faster than that. But it does require some memory. So this now takes us to a new, we've got to decide which path we're going down, essentially. You can either optimize for memory, where it may take more processor cycles to check each number, but you don't have to store lots of values. Or you can do what we're going to do, which is optimize for speed, but that sacrifices lots of memory because you have to store lots and lots of numbers if you're calculating up to a high limit. So essentially what we're going to do is because of prime factors, all we need to do to check if a number's prime is try dividing it by prime numbers up to the square root of itself, instead of just every number. So let's add that in. So what we're going to do is for test num in prime list. But now it's not going to stop when it gets to the square root. So now we'll also say if test num is greater than num squared, then break. We're not, of course, that wouldn't mean it's prime, but we still need to break out the loop. Let's see if this works. 1229. What's happened? It's taking longer now. That's because I've squared the wrong thing. Now, what we'll do is for now we'll just square root this. There we go. It's not actually really any faster. But let's see if it is faster. What we'll do is we'll change it back to what it was before. What was it? I'll comment this out and then add it back in. In range, we're going from 2 up to num squared plus 1, I think it was. Oh no, it's square root of num, wasn't it? Now what? Honestly, just will not leave me alone. There we go. So we might notice more of a difference using this prime method if we make our limit a bit higher. So let's try finding all the prime numbers up to 1,000,000. Now it's actually going to take some time. So trying to divide by every integer from 2 up to the square root of the value we're checking takes just under 5.5 seconds. But let's instead just try to divide by every prime number up to the square root of the number we're checking. There. It's not actually as much faster as you'd expect, but I decided to start off with the things that make the biggest difference because everybody likes an anticlimax. 3.6 seconds to calculate the first 1,000,000 primes. I don't think that's too bad. So I do actually have more optimisations that can be made. So that took us 3.6 seconds. The fastest program I've been able to make using the same principles takes under a second. But a lot of these optimisations are less mathematical and more to do with Python, essentially. So let's run through a few of those and see if we can get our program anywhere near to 1 second. So the first thing to do is remove 2, because what it's doing is it's trying to divide every single number by 2 that it's checking, and that is a waste of time because we know the multiples are only odd. So let's see how much time that saves us. About a bit over 1/10 of a second. That's not too bad. Let's see what else I've changed. Right, this one will probably save quite a lot of time. So we have a for loop in a for loop, which means the most critical stuff for the speed of our computation are these two if statements. But this one is finding the square root of a number every single time, and that's getting run probably at least 1,000,000 times. Square roots are very computationally demanding to calculate, And what we can actually do is simply change that to a squared here, and that should be faster. No. So instead, let's try something even sneakier, because in Python, when we use this power symbol, that doesn't necessarily mean this is an integer, which means the interpreter's running code that could deal with a floating point value here. But we know all we need to do is square it, and of course squaring is the same as multiplying by itself. Let's see if that's any faster. There we go, look at that. Under 2 seconds now. Let's see what else we can do. Right, so the next one is quite sneaky. I'm not sure if it's going to make much difference, but we can change this to an elif. Let's see if that does much. Nothing noticeable. Right, so the next one is a bit of a quirk of programming. 0 is equivalent to a Boolean false, and anything other than 0 is true. So instead of saying, is this equal to 0, we can just say, if not this. Watch. It's not meant to be slower. There we go, faster. This is where it would be nice to be running this code on something a little more consistent with its timing, but who cares? That is a little bit faster. So every optimization that could be made from now on that I've made on my other program are purely down to strange quirks of an interpreted programming language. So I will stop hiding it and I will show you my fast program. And the most substantial difference here is that everything is as compact as possible. No spaces here, no spaces there, single letter variable names. And that's because Python is interpreted, it slowly reads through your code. So if you give it less to read through, it'll be faster. There isn't much else that's different in this. But let's see. We're calculating primes up to 1,000,000. I've also defined it as a function, which I found to be slightly faster. There we go, under a second. Now in the next video, I will show you a slightly different technique I've thought of for providing a list of prime numbers. And that also has a few exciting ways of optimizing it. But that is for the next video, so stay tuned. Bye.